145. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Exercise 4.4.4. Are each of the following formulas valid, i.e., true for all? Interpretations. Remember that the relation names are just names. In the formula, don't assume the name has to have any bearing on their interpretation. For arbitrary A and B in the domain, 8 leastesweisias, A, B. 8 leastesweisias, B, A. For arbitrary A in the domain, prime, A, odd, A, prime, A. For arbitrary A and B in the domain, better than, A, B. Better than, B, A. For each, if it is true or false under all interpretations, prove that. For these small examples, a truth table will probably be easier than using Boolean algebra or inference rules. Otherwise, give an interpretation in which it is true, and one in which it is false. Note, as always, look at trivial and small test cases first. Here, try domains with 0, 1, or 2 elements, and small relations. Exercise 4.4.5. Suppose we wanted to represent the count of neighboring pirates with a binary relation, such that when location A has 2 neighboring pirates, pirates next to A, 2, will be true. Of course, pirates next to A, 1, would not be true in this situation. These would be analogous with the propositional Waterworld propositions A has 2 and A has 1, respectively. 1. If we only allow binary relations to be subsets of a domain crossed with itself, then what must the domain be for this new relation? Pirates next to 2. If we further introduced another relation, is number, what is a formula that would help distinguish intended interpretations from unintended interpretations? That is, give a formula that is true under all our intended interpretations of pirates next to but is not true for some nonsense interpretations we want to exclude. This will be a formula without an analog in the water world. Domain axioms, propositional axioms for water world, page 171. 146. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Exercise 4.4.6. Determine whether the relation R on the set of all people is reflexive, anti-reflexive, symmetric, anti-symmetric, and transitive, where A, B, are if and only if 1A is older than B, 2A is at least as old as B, 3A and B are exactly the same age, 4A and B have a common grandparent, 5A and B have a common grandchild. Exercise 4.4.7. For each of the following, if the statement is true, explain why, and if the statement is false, give a counterexample relation. 1. If R is reflexive, then R is symmetric. 2. If R is reflexive, then R is anti-symmetric. 3. If R is reflexive, then R is not symmetric. 4. If R is reflexive, then R is not anti-symmetric. 5. If R is symmetric, then R is reflexive. 6. If R is symmetric, then R is anti-reflexive. 7. If R is symmetric, then R is not anti-reflexive. 4.4.2 Quantifiers. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Exercise 4.4.8. Let P, X, be the statement has been to Prague, where the domain consists of your classmates. 1. Express each of these quantifications in English. X, P, X. 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 2. Which of these mean the same thing? 147. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. Exercise 4.4.9. Let C, X, be the statement X has a cat. Let D, X, be the statement X has a dog, and let F, X, be the statement X has a ferret. Express each of these statements in first-order logic using these relations. Let the domain be your classmates. 1. A classmate has a cat, a dog, and a ferret. 2. All your classmates have a cat, a dog, or a ferret. 3. At least one of your classmates has a cat and a ferret, but not a dog. 4. None of your classmates has a cat, a dog, and a ferret. 5. For each of the three animals, there is a classmate of yours that has one. Exercise April 4, 10. Determine the truth value of each of these statements if the domain is all real numbers. Where appropriate, give a witness. 1, 2, 3, 4. 4.4.3 Interpreting First-Order Formulas. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Exercise April 4, 11. Let P, X, Q, X, R, X, and S, X, be the statements X is a duck, X is one of my poultry, X is an officer, and X is willing to waltz, respectively. Express each of these statements using quantifiers, logical connectives, and the relations P, X, Q, X, R, X, and S, X. 1. No ducks are willing to waltz. 2. No officers ever decline to waltz. 3. All my poultry are ducks. 4. My poultry are not officers. 5. Does the fourth item follow from the first three taken together? Argue informally, you don't need to use the algebra or inference. Rules for first-order logic here. 148. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Exercise April 4, 12. You come home one evening to find your roommate exuberant, because they have managed to prove that there is an even prime number bigger than 2. More precisely, they have a correct proof of y, p, y, y, 2, e, y, for the domain of natural numbers, with p interpreted as is prime, and e interpreted as is even. While they are celebrating their imminent fame at this amazing mathematical discovery, you ponder 1. And realize the formula is indeed true for that interpretation. Briefly explain why. You don't need to give a formal proof using Boolean algebra or inference rules, just give a particular value for y, and explain why it satisfies the body of y. 2. Is the formula still true when restricted to the domain of natural numbers 2 or less? Briefly explain why or why not. 3. Is the formula still true when restricted to the empty domain? Briefly explain why or why not. 4. Give a formula that correctly captures the notion there is an even prime number bigger than 2. Exercise April 4, 13. For the sentence xy a, x, b, x, y, a, y, state whether it is true or false, relative to the following interpretations. If false, give values for x and y witnessing that 1. The domain of the natural numbers, where a is interpreted as even, and b is interpreted as equals. 2. The domain of the natural numbers, where a is interpreted as even, and b is interpreted as is an integer divisor of 3. The domain of the natural numbers, where a is interpreted as even, and b is interpreted as is an integer multiple of 4. The domain of the Booleans, true, false, where a is interpreted as false, and b is interpreted as equals. 5. The domain of Waterworld locations in the particular board where locations y and z contain pirates, but all other locations are safe. The relation symbol a is interpreted as unsafe, and b is interpreted as neighbors. 6. All Waterworld boards, where a is interpreted as safe, and b is interpreted as neighbors. That is the formula valid for Waterworld. 149. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Exercise April 4, 14. Translate the following conversational English statements into first-order logic, using the suggested predicates, or inventing appropriately named ones if none provided. You may also freely use equal, which we'll choose to always interpret as the standard equality relation. 1. All books rare and used. This is claimed by a local bookstore. What is the intended domain? Do you believe they mean to claim all books rare or used? 2. Everybody who knows that UFOs have kidnapped people knows that Agent Mulder has been kidnapped. Is this true, presuming that no UFOs have actually visited Earth yet? Exercise April 4, 15. Write a formula for each of the following. Use the two binary relations is for and is against and domain of all people. All for one, and one for all. We'll take one to mean one particular person, and moreover, that both ones are referring the same particular person, resulting in there is one whom everybody is for, and that one person is for everybody. 13. If you're not for us, you're against us. In aphorisms, you is meant to be an arbitrary person. Consider using the word one instead. Furthermore, we'll interpret us as applying to everybody. That is, one always believes that if one is not for me, then one is against me. The enemy of your enemy is your friend. By your enemy we mean somebody you are against, and similarly, your friend will mean somebody you are for. Be careful, this may be different than somebody who is against EJF or you. Somebody has an enemy. We don't know of an aphorism expressing this. 14. Two interpretations are considered fundamentally the same, or isomorphic, if you can map one interpretation to the other simply by a consistent renaming of domain elements. Exercise April 4, 16. Find two fundamentally different interpretations that satisfy the statement, there exists one person who is liked by two people. 150. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. Exercise April 4, 17. For the Four Musketeer formulas from a previous exercise, exercise April 4, 15, find three fundamentally different interpretations of is for, which satisfy all the formulas on a domain of three people. Depict each of these interpretations as a graph. Draw three circles, nodes, representing the three people, and an arrow, edge, from a person to each person they like. You can glance at Rosen section 9.1. Figure 8 for an example. Note, one of the interpretations is unintuitive in that is for and is against don't correspond to what we probably mean in English. Exercise April 4, 18. Translate the following statements into first-order logic. The domain is the set of natural numbers, and the binary relation kth, k, n. I indicates whether or not the kth number of the sequence is n. For example, the sequence 5, 7, 5 is represented by the relation kth equal 0, 5, 1, 7, 2, 5. You can also use the binary relations equal, and, but no others. You may assume that kth models a sequence. No index k is occurs multiple times, thus excluding kth equal 0, 5, 1, 7, 0, 9. Thus, kth is a function, as in a previous example representing an array as a function, example 4.8. Also, no higher index k occurs without all lower numbered indices being present, thus excluding kth equal 0, 5, 1, 7, 3, 9, 1. The sequence is finite. 2. The sequence contains at least 3 distinct numbers, for example, 5, 6, 5, 6, 7, 8, but not 5, 6, 5, 6. 3. The sequence is sorted in non-decreasing order, for example, 3, 5, 5, 6, 8, 10, 10, 12. 4. The sequence is sorted in non-decreasing order, except for exactly one out-of-order element, for example, 20, 30, 4, 50, 60. 151. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Exercise April 4, 19. Some binary relations can be viewed as the encoding of a unary function, where the first element of the ordered pair represents the function's value. For instance, in a previous exercise, exercise 4.4.2, we encoded the binary function addition as a ternary relation adds to 1. Give one example of a binary relation which does not correspond to the encoding of a function. 2. Write a first-order formula describing the properties that a binary relation R must have to correspond to a unary function. Exercise April 4, 20. Alternation of quantifiers. Determine the truth of each of the following sentences in each of the indicated domains. Note: to help yourself, you might want to develop an English version of what the logic sentences say. Start with the inner formula, talking about people X, Y, Z, then add the quantifier for Z to get a statement about people X, Y, and repeat for the other two quantifiers. 4 sentences. 1, 2, 3, 4. 4 domains. 1. The empty domain. 2. A world with one person, who likes herself. 3. A world with Yorick and Zelda, where Yorick likes Zelda, Zelda likes herself, and that's all. 4. A world with many people, including CJ, Catherine Zeta-Jones, JC, John Cusack, and Jr., Julia Roberts. Everybody likes themselves. Everybody likes JC, everybody likes CJ except Jr., everybody likes Jr. except CJ and IB. Any others may or may not like each other, as you choose, subject to the preceding. You may wish to sketch a graph of this likes relation, similar to Rosen section 9.1 figure 8. Determine the truth of all 16 combinations of the 4 statements and 4 domains. 152. Download for free at https://contents/383d4b872d7b454e99fe2eaa43a8ff at 2020. 4.4.4 Modeling. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Exercise April 4, 21. Translate the following into first-order logic: raspberry sherbet with hot fudge, RSHF, is the tastiest dessert. Use tastier as your only relation. What is the intended domain for your formula? What is a relation which makes this statement true? One which makes it false? Exercise April 4, 22. Even allowing for elision, the list of Waterworld domain axioms. Section 6.6 is incomplete, in a sense. The game reports how many pirates exist in total, but that global information is not reflected in the propositions or axioms. We had the same problem. Exercise February 5, 13, with the propositional logic domain axioms. 1. First, assume we only use the default Waterworld board size and number of pirates, i.e., FVE. What additional axiom or axioms do we need? 2. Next, generalize your answer to model the program's ability to play the game with a different number of pirates. What problem do you encounter? 153. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Exercise April 4, 23. The puzzle game of Sudoku is played on a 9x9 grid, where each square holds a number between 1 and 9. The positions of the numbers must obey constraints. Each row and each column has each of the 9 numbers. Each of the 9 non-overlapping 3x3 square subgrids has each of the 9 numbers. Like Waterworld, throughout the game, some of the values have not been discovered, although they are determined. You start with some numbers revealed, enough to guarantee that the rest of the board is uniquely determined by the constraints. Thus, like in Waterworld, when deducing the value of another location, what has been revealed so far would serve as premises in a proof. Fortunately, there are the same number of rows, columns, subgrids, and values. So, our domain is 1, 2, 3, 4, 5, 6, 7, 8, 9. To model the game, we will use the following relations. Value R, C, V, indicates that at row R, column C is the value V. V equal W is the standard equality relation. Subgrid G, R, C, indicates that subgrid G includes the location at row R, column C. Provide domain axioms for Sudoku, and briefly explain them. These will model the row, column, and subgrid constraints. In addition, you should include constraints on our above relations, such as that each location holds one value. 4.4.5 Reasoning with equivalences. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0 Exercise April 4, 24. Some of the first-order equivalences, page 168, are redundant. For each of the following, prove the equivalence using the other equivalences. 1. 2. Assuming a non-empty domain. 154. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Exercise April 4, 25. We can characterize a prime number as a number n satisfying. Using the equivalences for first-order logic, show step by step that this is equivalent to the formula. Do not use any arithmetic equivalences. Exercise April 4, 26. A student claims that by the distribution of quantifiers, this is actually trying to do two steps at once. Rewrite this as the two separate intended steps. Determine which is wrong, and describe why that step is wrong. Exercise April 4, 27. Simplify the formula so that the body of each quantifier contains only a single atomic formula. Definition: well-formed formula, WFF, for first order logic, involving that quantified variable. Provide reasoning for each step of your simplification. 4.4.6 Reasoning with Inference Rules. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Exercise April 4, 28. Prove that syllogisms are valid inferences. In other words, show that x 155. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Exercise April 4, 29. What is wrong with the following proof of XE, X, E, C? 1. Subproof. 1. A premise for subproof. 1 B-E, C, Alim, line 1a. 2. Intro, line 1. Exercise April 4, 30. Using the inference rules, formally prove the last part of the previous problem about ducks and such. Exercise April 4, 11. Exercise April 4, 31. Give an inference rule proof of X, fruit, X, has method, test Y, X, Y, apple, Y, fruit, Y, Z, apple, Z, has method, test Y, Z. Exercise April 4, 32. 1. Prove the following: X, P, X, Y, P, Y, Q, Y, Z, Q, Z. 2. Your proof above used intro. Why can't we replace that step with the formula ZQ, Z, with the justification intro? 3. Describe an interpretation which satisfies the proof's premises, but does not satisfy Z, Q, Z. 4.4.7 Solutions to exercises in chapter. Available under Creative Commons Sharealike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. Solution to exercise 4.1.1.1. The Q, somebody, suggests one person who exists, we'll call them P for popular, P. Now we need to fill in the dots with everybody likes P, to get P. X likes X, P. Solution to exercise 4.1.1.2. 156. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. The Q, everybody, suggests a universal, we'll call them J for J. Do, J. Now, we need to fill in the dots with somebody likes J, to get J, X, likes X, J. Note that this formula is just like the preceding somebody likes everybody example. Example 4.3, except that the quantifiers have been swapped, and different variable names were used, a superficial difference. Solution to exercise 4.1.1.3. Evenness is a straightforward translation from an integer n is even, if it is twice some other integer k, even, n, k, n equal to k. Note that by this standard definition, 0 is even. There are many equivalent ways to define primality, just as there are many algorithms for checking primality. One straightforward solution is non-composite, n, j, k equal n, j equal 1, k equal 1. Well, this is almost expresses prime, except that n equal 1 satisfies this formula. A mathematician points out that just as 0 is neither positive nor negative, 1 is neither prime nor composite, as stated this formula actually captures non-composite. Oops. There are several ways to upgrade this to exactly capture prime. Aside, one is called a unit. If we consider the domain of all integers, not just natural numbers, the idea of primality still makes sense. -17 is also prime, and -1 is also another unit. Similarly, considering the domain of complex integers a, b, a plus by a, z, b, z, could be written z plus zi, then I and I are also units. How might we generalize our definition of prime, to work in these further interpretations? A similar, equivalent formula to the above is non-composite, n. Solution to exercise 4.1.1.4. Solution to exercise 4.1.1.5. We need a new relation that combines the syntax of and size. The result would look like less than size, I, a. This assumes the new relation has the obvious intended definition. Solution to exercise 4.1.1.6. Solution to exercise 4.1.1.7. There are various solutions, but they all must capture the same idea. There exists exactly one unsafe neighbor. This solution states that in two parts. there exists an unsafe neighbor, you. Every unsafe neighbor is you. Together, these two parts imply there is only one such you. Solution to exercise 4.2.1.1. 157. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. 1. 2. Definition of. 3. Distribution of over. 4. Complementation of. 5. Definition of. Solution to exercise 4.3.1.1. In line 4, intro requires that variable being generalized, q, be arbitrary. It was introduced in line 2 by Alim, so that's okay. For example, we could have used intro on line 3 to reintroduce the 20if or just eliminated. But, q was free when we used Alim on line 3, and this makes the variable no longer arbitrary. Line 3's choice of p may depend on q, and a variable is only arbitrary if it is free of any such constraints. Solution to exercise 4.4.5. 1. The relation needs to accept locations as well as numbers, so the domain is L. N, where L is the set of Waterworld locations. Alternatively, you could use 0, 1, 2, 3 instead of N, the set of all natural numbers. 2. The difficulty is that it's possible to ask about nonsensical combinations like Pyrates nexto, 17, 2 and Pyrates nexto, W, B. Adding is number, any. Interpretation would be expected to satisfy, for arbitrary A and B, Pyrates nexto. A, B, is number. B, is number. A, B. Aside, more interestingly though, imagine we did interpret Pyrates nexto over the domain N only. We could then pretend that the locations, instead of being named A, Z, were just numbered 1, 24. While this representation doesn't reflect how we model the problem, it is legal. Exercise for the reader, write a formula which excludes relation Pyrates nexto which can't match this convention. Solution to exercise April 4, 16. 1. Interpretation that satisfies this is a domain of 3 people Alice, Bob, Charlie. With the likes relation, Alice, Bob, Bob, Bob. Bob is liked by 2 people, so it satisfies the statement. Here's another interpretation that is the same except for renaming, and thus not fundamentally different, a domain of 3 people Alyssa, Bobby, Chuck, with the likes relation, Chuck, Alyssa, Alyssa, Alyssa. With the substitutions Chuck Alice and Alyssa Bob, we see that the underlying structure is the same as before. Here's an interpretation that is fundamentally different, a domain of 3 people Alice, Bob, Charlie, with the likes relation, Charlie, Bob, Alice, Bob. No matter. 158. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. How you rename, you don't get somebody liking themselves, so you can see its underlying structure is truly different than the preceding interpretations. English is fuzzy enough that it is unclear whether 1 and 2 are meant as exact counts. The above two examples each assume they are. Aside, if we change the statement slightly to add a comma, there exists one person who is liked by two people, we arguably change the meaning significantly. The now independent first clause arguably means there is only one person existent in total, so the overall statement must be false. There's a quick lesson in the difference between English dependent and independent clauses. Solution to exercise April 4, 28. 1 premise. 2 premise. 3 Elim, line 1. 4 Elim, lines 2, 3. 159. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Chapter 5 Conclusion. Acknowledgements. 5.1 Logic, looking back. 5.1.1 Why didn't we begin with quantifiers all along? Available under Creative Commons Share-alike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. We saw 3 stages of logics. Propositional logic, with formulas like Dick likes Jane, Jane likes Dick. While the propositions are named suggestively, nothing in the logic enforces a relation. Among these, it is equivalent to AB. Predicate logic, where variables and constants can express a connection between different parts of the formula, likes, y, x, likes, x, y. Predicate logic introduced the idea of variables, and required domains and interpretations to determine truth. But it can't bind variables, and thus requires an interpretation of x and y to evaluate. First-order logic, which included 2 quantifiers to bind variables, y, x, likes y, x, likes, x, y. So why, you might ask, didn't we just start out with first-order logic in the first lecture? One reason, clearly, is to introduce concepts one at a time. Everything you needed to know about one level was needed in the next, and then some. But there's more. By restricting our formalisms, we can't express all the concepts of the bigger formalism. But we can have automated ways of checking statements or finding proofs. In general, this is a common theme in the theory of any subject, determining when and where you can, or need to, trade of expressibility for predictive value. For example, linguistics, having a set of precise rules for, say, Tagalog grammar allows you to determine what is and isn't a valid sentence. Details of the formal grammar can reveal relations to other languages which aren't otherwise so apparent. On the other hand, a grammar for any natural language is unlikely to exactly capture all things which native speakers say and understand. If working with a formal grammar, one needs to know what is being lost and what is being gained. Dismissing a grammar as irrelevant because it doesn't entirely reflect usage is missing the point of the grammar. conversely, condemning some real-life utterances as ungrammatical, and ignoring them, forgets that the grammar is a model which captures many, if not all, important properties. Of course, any reasonable debate on this topic respects these two poles and is actually about where the best trade-off between them lies. 160. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Psychology, say, Piaget. 2. Might propose 4 stages of learning in children. It may not trade of total accuracy, for, say, clues of what to look for in brain development. Physics, modern pedagogy must trade of quantum accuracy for Newtonian approximations. Researchers exploring fields like particle physics must trade of exact simulations for statistical, stochastic, approximations. Understanding the theoretical foundations of a field is often critical for knowing how to apply various techniques in practice. 5.1.2 Logic and Everyday Reasoning. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. We've looked at the impreciseness and ambiguity of natural language statements, but these are not the only problems hidden in natural language arguments. The following illustrates a common form of hidden assumption, saying the 10th reindeer of Santa Claus is implies the existence some 10th reindeer. More subtly, humans use much more information than what is spoken in a conversation. Even aside from body language, consider a friend asking you, "Hey, are you hungry?" While as a formal statement this doesn't have any information, in real life it highly suggests that your friend is hungry. A much more blatant form of missing information is when the speaker simply chooses to omit it. When arguing for a cause, it is standard practice to simply describe its advantages, without any of its disadvantages or alternatives. Aside, economists measure things not in cost, but opportunity cost, the price of something minus the benefits of what you'd get using the price for something else. For example, for $117 million the university can build a new research center. But what else could you do on campus with $117 million? Historically, logic and rhetoric, the art of persuasion through language, are closely linked. 5.1.3 Other logics. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. You've now been introduced to 2 logics, propositional and first order. But the story does not have to end here. There are many other logics, each with their uses. 161. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. 5.1.3.1 Limitations of first-order logic's expressiveness. Available under Creative Commons Share-alike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. We can make first-order sentences to express concepts as vertices A and B are connected by a path of length 2, as well as by a path of length 3, length 4, etc. Note: write a couple of these sentences. But trying to write vertices A and B are connected by a path of any length isn't obvious. In fact, it can be proven that no first-order sentence can express this property. Nor can it express the closely related property the graph is connected without reference to two named vertices A and B. What about second-order logic? It has a bigger name, whatever it means. Perhaps it can express more properties? What exactly is second-order logic? In first-order logic, quantifiers range over elements of the domain. There exist numbers x and y. In second-order logic, you can additionally quantify over sets of elements of the domain. There is a set of numbers, such that. Example 5.1. For instance, for all vertices x and y, there exists a set of vertices. Call the set red. The red vertices include a path from x to y. More precisely, every red vertex has exactly two red neighbors, or it is x or y, which each have exactly one red neighbor. Is this sentence true? Exactly when the graph is connected. Why does this description of red vertices not quite correspond to just the vertices on a path from x to y? An interesting phenomenon. There are some relations between how difficult it is to write down a property, and how difficult to compute it. How might you try to formalize the statement, "There is a winning strategy for chess"? A shortcoming of first-order logic is that it is impossible to express the concept path. This can be proven, though we won't do so here. Thus, some other logics used to formalize certain systems include: as mentioned, second-order logic is like first-order logic, but it also allows quantification over entire relations. Thus, you can make formulas that state things like for all relations R, if R is symmetric and transitive, then. While less common, we could continue with third order, fourth order, etc. Temporal logic is based on quantification over time. This is useful to describe how a program's state changes over time. In particular, it is used for describing concurrent program specifications and communication protocols, sequences of 162. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Communications steps used in security or networking. See, for example, Teach Logic's Model Checking Module 3. Linear logic is a resource-aware logic. Every premise must be used, but it may be used only once. This models, for example, how keyboard input is usually handled. Reading an input also removes it from the input stream, so that it can't be read again. 5.1.4 Logic in Computer Science. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Logics provide us with a formal language useful for specifying properties unambiguously, proving that programs and systems do, or don't, have the claimed properties, and gaining greater insight into other languages such as database queries. 4. Programming language type systems are a great example of these first 2 points. The connectives allow us to talk about pairs and structures, X and Y, unions, X or Y, and functions. If you give the program a X, it produces a Y. The generics in Java, C++, and C are based upon universal quantification, while wildcards in Java are based upon existential quantification. One formalization of this strong link between logic and types is called the Curry-Howard isomorphism. Compilers have very specific logics built into them in order to optimize your code. Analyses check what properties your code has. For example, are variables B and C needed at the same time, or can they be stored in the same hardware register? More generally, it would be great to be able to verify that our hardware and software designs were correct. First, specifying what correct means requires providing the appropriate logical formulas. With hardware, automated verification is now part of the regular practice. However, it is so computationally expensive that it can only be done on pieces of a design, but not, say, a whole microprocessor. With software, we also frequently work with smaller pieces of code, proving individual functions or algorithms correct. However, there are 2 big interrelated problems. Many of the properties we'd like to prove about our software are undecidable. It is impossible to check the property accurately for every input. Also, specifying full correctness typically requires extensions to first-order logic, most of which are incomplete. As we've seen, that means that we cannot prove everything we want. While proving hardware and software correct has its limitations, logic provides us with tools that are still quite useful. For an introduction to one approach used in verification, see Teach Logics. Model Checking Module 163. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. 5.2 Acknowledgements. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. The Teach Logic project is the work of many contributors, and was made possible through an NSF SCICE grant. Major contributors and grant principal investigators are Moshe Vardi, Rice University; Matthias Felleisen, Northeastern University; Ian Barland, Rice University; Fokshan Kolaitis, University of California at Santa Cruz. John Greiner, Rice University. In addition, Paul Steckler implemented the base module's Waterworld game. 10. Students who helped contribute to various Teach Logic modules include: chronologically, Peggy Fiddleman, Justin Garcia, Brian Cohen, Sarah Trowbridge, Brian Cash, Fuking Jack Chi, Ben McMahon. Teach Logic has also been influenced by the BEASM project, headed by Rex Page of Oklahoma University. In particular, the base module owes both some overall structure and specific details to BEASM. Janice Bordeaux, from the Engineering Dean's Office at Rice University, assisted with developing classroom assessment tools. 164. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Chapter 6 Appendices and Reference Cheats. 6.1 Propositional Equivalences. Available under Creative Commons Share-alike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. The following lists some propositional formula equivalences. Remember that we use the symbol as a relation between two WFFs, not as a connective inside a WFF. In these, and are metavariables standing for any WFF. Double complementation. Complement, true false. Identity, false true. Dominance, true true false false. Idempotency. Absorption. Redundancy. De Morgan's laws. Associativity. Commutativity. Distributivity. Table 6.1 Propositional Logic Equivalences. 165. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Equivalences for implication are omitted above for brevity and for tradition. They can be derived using the definition AB. Example 6.1. For example, using identity and commutativity, we have true B, false B, false B. 6.2 Propositional Inference Rules. Available under Creative Commons Share-alike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. Abbreviation name. If you know all of, then you can infer intro and introduction, elim and elimination, left and elimination, right, intro or introduction, left or introduction, right, elim or elimination. Table 6.2 Our Propositional Inference Rules. 166. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. Abbreviation name. If you know all of, then you can infer. Intro. If. Introduction. Elim. If elimination. Modus ponens. False intro. False introduction. False elim. False elimination. Reductio ed. Absurdum, v. 1. Ra. Reductio ed. Absurdum, v. 2. Intro. Negation. Introduction. Elim. Negation. Elimination. Case. Elimination. Left. Case elim. Case. Elimination. Right. Table 6.2 Our Propositional Inference Rules. 167. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. As usual, are metavariables standing for any WFF. This is by no means the only possible inference system for propositional logic. Aside, this set of inference rules is based upon discrete mathematics with a Compute T by Hall and O'Donnell, Springer, 2000, and the BEASM project. 6.3 First-order equivalences. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. The following equivalences are in addition to those of propositional logic, propositional L equivalences, page 165. In these, and each stand for any WFF, but stands for any WF with no free occurrences of X. Equivalence variant. Complementation of quantifiers X. Interchanging quantifiers X, Y, X, Y, X, Distribution of quantifiers X. Distribution of quantifiers with non-empty domain X. Table 6.3 First-order logic equivalences. 168. Download for free at https://383D4B8722D7B454E99FE2EAA43A8FF at 2020. Equivalence variant. X. Renaming X, Y. Simplification of quantifiers with non-empty domain x, x. Simplification of quantifiers with empty domain. X, true, x, false. Table 6.3 First order logic equivalences. When citing distribution of quantifiers, say what you're distributing over what. For example, distribute over with being x free. In renaming, the notation xy means with each free occurrence of x replaced by y. It is a metaformula. When writing any particular formula you don't write any brackets, and instead just do the replacement. This set of equivalences isn't actually quite complete. For instance, is equivalent to true, but we can't show it using only the rules above. It does become complete. 5. If we add some analogues of the first order inference rule, page 169. Replacing with and carrying along their baggage of arbitrary and free to substitute in. 6.4 First order inference rule. Available under Creative Commons Sharealike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. The following are in addition to those of propositional inference rules, page 166. 169. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Abbreviation name. If you know all of, then you can infer. Intro. Introduction. Y. Arbitrary, p. 99. XYX. X. T is any term that is free to be replaced in elim. Elimination. Domain non-empty. XT. T is any term in that is free to be replaced. Intro. Introduction. Domain non-empty. XTX. Where T is arbitrary. X. C is a new constant in the proof. Elim. Elimination. C does not occur in the proofs. Conclusion. XC. Table 6.4 Our first order inference rules. As usual, we use as a metavariable to range over first order WFFs. Similarly, T is a metavariable for first order terms, and C is a metavariable for domain constants. The 170. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. Notation. VW means the formula but with every appropriate note, P99. Occurrence of V replaced by W. As discussed in the lecture notes, a variable is arbitrary unless a variable is not arbitrary if it is free in an enclosing premise. A variable is not arbitrary if it is free after applying elim either as the introduced witness C, or free anywhere else in the formula. The usual way to introduce arbitrary variables is during elim, WJO later using it in Elim. As a detail in Elim and intro, the term t must be free to replace the variable x in. This means that it is not the case that both t contains a variable ch1tif in, and that x occurs free within that ch1tif. In short, the bound variable names should be kept distinct from the free variable names. Also, only free occurrences x get replaced. The restriction in Elim on C being new is similar. 6.5 Propositional Axioms for Waterworld. Available under Creative Commons Sharealike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. We summarize the details of how we choose to model Waterworld boards in propositional logic, exactly what propositions we make up, and the formal domain. Axioms which capture the game's rules. The board is fx'd at 6 times 4, named A, Z, with I and O omitted. 171. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Figure 6.1 A Sample Waterworld Board. 6.5.1 Propositions. Available under Creative Commons Sharealike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. There are a myriad of propositions for Waterworld, which can be grouped. Whether or not a location contains a pirate, A. Unsafe, B. Unsafe, Z. Unsafe. Whether or not a location contains no pirate, A. Safe, B. Safe, Z. Safe. 172. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Aside, yes, using the intended interpretation, these are redundant with the previous ones. Some domain axioms below will formalize this. Propositions indicating the number of neighboring pirates to a location: A has 0, A has 1, A has 2, B has 0, B has 1, B has 2, H has 0, H has 1, H has 2, H has 3, Z has 0, Z has 1. These are all true or false propositions. There are no explicit numbers in the logic. A domain axiom below will assert that whenever, say, B has 1 is true, then B has 0 and B has 2 are both false. Aside, there is no proposition A has 3, since location A has only 2 neighbors. Similarly, there is no proposition B has 3. We could have chosen to include those, but under the intended interpretation they'd always be false. These propositions describe the state of the underlying board, the model, and not our particular view of it. Our particular view will be reflected in which formulas we'll accept as premises. So we'll accept A has 2 as a premise only when A has been exposed and shows a 2. 6.5.2 The domain axioms. Available under Creative Commons Share-alike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. Axioms asserting that the neighbor counts are correct. Count of 0. A0, A has 0. B, safe. G, safe. H0, H has 0. G, safe. J, safe. P, safe. Z0, Z has 0. Y, safe. Count of 1. A1, A has 1. B, safe. G, unsafe. B, unsafe. G, safe. H1, H has 1. G, safe. J, safe. P, unsafe. G, safe. J, unsafe. P, safe. G, unsafe. J, safe. P, safe. Z1, Z has 1. Y, unsafe. Count of 2. A2, A has 2. B, unsafe. G, unsafe. H2, H has 2. G, safe. J, unsafe. P, unsafe. G, unsafe. J, safe. P, unsafe. G, unsafe. J, unsafe. P, safe. There aren't any such axioms for locations with only one neighbor. 173. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Count of 3. H3, H has 3. G, unsafe. J, unsafe. P, unsafe. There aren't any such axioms for locations with only one or two neighbors. Axioms asserting that the propositions for counting neighbors are consistent. A has 0. A has 1. A has 0. A has 1. A has 1. A has 0. B has 0. B has 1. B has 2. B has 0. B has 1. B has 2. B has 1. B has 0. B has 2. B has 2. B has 0. B has 1. H has 0. H has 1. H has 2. H has 3. H has 0. H has 1. H has 2. H has 3. H has 1. H has 0. H has 2. H has 3. H has 2. H has 0. H has 1. H has 3. H has 3. H has 0. H has 1. H has 2. Axioms asserting that the safety propositions are consistent. A safe. A unsafe. A safe. A unsafe. Z safe. Z unsafe. Z safe. Z unsafe. This set of axioms is not quite complete, as explored in an exercise February 5, 13. As mentioned, it is redundant to have both A safe and A unsafe as propositions. Furthermore, having both allows us to express inconsistent states, ones that would contradict the safety axioms. If implementing this in a program, you might use both as variables, but have a safety check function to make sure that a given board representation is consistent. Even better, you could implement Waterworld so that these propositions wouldn't be variables, but instead be calls to a lookup, accessor functions. These would examine the same internal state, to eliminate the chance of inconsistent data. Using only true or false propositions, without recourse to numbers makes these domain axioms unwieldy. Later, we'll see how relations, page 105, and syntax and semantics of quantifiers, page 123, help us model the game of Waterworld more concisely. 174. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. 6.6 First Order Axioms for Waterworld. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. We summarize the details of how we choose to model Waterworld boards in first order logic, exactly what relations we make up, and the formal domain axioms which capture the game's rules. This will follow almost exactly the same pattern as our Waterworld model in Propositi. Onal Axioms for Waterworld, page 171. However, we will take advantage of the additional flexibility provided by first-order logic. Rather than modeling only the default 6x4 Waterworld board, we will be able to model any board representable by our relations. This will allow boards of any size and configuration, with one major constraint: each location can have at most 3 neighboring pirates. 6.6.1 Domain and Relations. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. Our domain is simply the set of all board locations. This set can be arbitrarily large, even infinite. The board configuration is given by the binary neighbor relation NHBR. The next relations correspond directly to the propositions, page 172, in the propositional logic model. Whether or not a location contains a pirate, safe. This is a unary relation. Aside, we choose not to include a redundant relation unsafe. Unary relations indicating the number of neighboring pirates, HAS0, HAS1, HAS2, and HAS3. Aside, thus, we have our restriction to 3 unsafe neighbors. This will also be reflected in our domain axioms below. See also this problem, exercise 3.5.1, for a discussion of how to avoid this restriction. In addition, to have encode the domain axioms for an arbitrary domain, we also need an equality relation over our domain of locations. As is traditional, we will use infix notation for this relation, for example, x equal y. Furthermore, we will allow ourselves to write x equal y as shorthand for x equal y. Thus, we do not need a distinct inequality relation. Note that these relations describe the state of the underlying board, the model, and not our particular view of it. Our particular view will be reflected in which formulas we'll accept as premises. So we'll accept HAS2, A, as a premise only when A has been exposed and shows a 2. 175. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. 6.6.2 The Domain Axioms. Available under Creative Commons Sharealike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. Many of our axioms correspond directly, albeit much more succinctly, with those. Section 6.5.2, The Domain Axioms, page 173, of the propositional model. In addition, we have axioms that specify that our neighbor and equality relations are self-consistent. Axioms asserting that the neighbor relation is anti-reflexive and symmetric. X NHBR, X, 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 Y, NHBR, X, Y, NHBR, Y, X. Axioms asserting that equal truly is an equality relation, i.e., it is reflexive, symmetric, and transitive. X, X equal X. X, Y, X equal Y, Y equal X. X, Y, Z, X equal Y, Y equal Z, X equal Z. Axioms asserting that the neighbor counts are correct. Each of these is of the form if location X has n neighboring pirates, then there are n distinct unsafe neighbors of X. And any other distinct neighbor X is safe. We use the equality relation to specify the distinctness of each neighbor. In addition, we want the implications to go the opposite way. Otherwise, each of HAS0, HAS1, HAS2, and HAS3 could always be false, while still satisfying the above. For brevity, we allied the details in the following list: X, Y, NHBR, X, Y, safe, Y, HAS0, X, X, HAS1, X, X, HAS2, X, X, HAS3, X. Axioms asserting that the neighbor counts are consistent, while redundant, including axioms like the following can be convenient: X, HAS0, X, HAS1, X, HAS2, X, HAS3, X, X, HAS1, X, HAS0, X, HAS2, X, HAS3, X. 176. Download for free at https://383d4b872d7b454e99fe2eaa43a8ff at 2020. X, HAS2, X, HAS0, X, HAS1, X, HAS3, X, X, HAS3, X, HAS0, X, HAS1, X, HAS2, X. Note that this set of axioms is not quite complete, as explored in an exercise, April 4, 22. 6.7 Browser supports. Available under Creative Commons Sharealike 4.0 International License, http creativecommons.org/licenses/by-sa/4.0. Caution: the information in this module is outdated. Please see my course L0 for a table of contents. Note: this page meant to be viewed with a Mathmel-enabled browser. If you see X, P, X, Y, P, Y as a nice version of for all x, p, x, exists. Y, p, y, v phi, you're doing okay, if you further see. As a nice version of, script AI script, you're set. If not, see our description of. Browser support, section 6.7. At Rice on the CSNet, use Mozilla. Preferably, use version 1.1, as currently available on Solaris 8 machines. On Frosty CS, version 1.1 is the default. On other Solaris 8 machines, version 1.1 is not yet the default, but available via IOPT1 Mozilla 11 Isunos 5 Ibn Mozilla. In general, to view TeachLogic web pages, you'll need a browser that supports the following features: Cascading Style Sheets, CSS. 11. Most recent browsers support CSS sufficiently well. MathML. L2. Some browsers support MathML sufficiently well. However, most, all, do not fully support Unicode Plain 1 numerical entity references, which includes most mathematical alphanumeric characters. Math-oriented fonts. L3. Which browsers support these features? The above links provide more details, but here's a summary of some browsers. Mozilla 14 and Netscape 15. Version 7.0, both work, except some characters. Unicode Plain 1, don't appear correctly. Internet Explorer L6 is not yet an option, even with the Math Player plugin. L7 to view MathML, i.e. won't display pages with some characters, Unicode Plain 1. Alternatively, PDF versions of the web pages are also provided via the base modules. Index 177. Download for free at https://383d4b8722d7b454e99fe2eaa43a8ff at 2020. Glossary. Available under Creative Commons Share-alike 4.0 International License, http Creative Commons s.org/licenses/by-sa/4.0. See completeness. If something really is true, the system is capable of proving it. Connective 1. The syntactic operator combining one or more logical expressions into a larger expression. 1. Example, two operators are and 2. A function with one or more Boolean inputs and a Boolean result, i.e., the meaning of a syntactic operator. 1. Example, the meaning of and, for example, as described by their truth tables. 2. Example, NAND, mnemonic, not and, written, takes in two Boolean values a and b, and returns true exactly when a b is not true, that is, a b. I interpretation. The interpretation of a formula is a domain, together with a mapping from the formula's relation symbols to specific relations on the domain. P proposition. A statement which can be either true or false. Example, your meal will include hash browns. Propositional variable. A variable that can either be true or false, representing whether a certain proposition is true or not. Example, HB's soundness. If the system claims to prove something is true, it really is true. Tautology. A WFF which is true under any truth assignment, any way of assigning true or false to the propositions. Example, A unsafe. Example, A/B. Term 1. A variable. Example, A, B. 2. A constant. Example, Waterworld location F, Kevin Bacon, or the number 3. 3. A function applied to one or more terms. 178. Download for free at https://383D4B872D7B454E99FE2EAA43A8FF at 2020. Example, successor, 3. Truth assignment. An assignment of a value, true or false, to each proposition being used. Example, for the formula AAB, one possible truth assignment is A equal true and B equal false. With that truth assignment, the formula is false. Truth table. A truth table for an expression has a column for each of its propositional variables. It has a row for each different true/false combination of its propositional variables. It has one more column for the expression itself, showing the truth of the entire expression for that row. U unsatisfiable. A WFF which is false under any truth assignment. Example, A unsafe. Example, A W well-formed formula, WFF. 1. A constant, true or false. If you prefer brevity, you can write T or F. 2. A propositional variable. 1. Example, A. 3. A negation, where is a WFF? 1. Example, C. 4. A conjunction, where N are WFFs. 1. Example, A, C. 5. A disjunction, where N are WFFs. 1. Example, C, A, C, or equivalently, C, A, C. 6. An implication, where N are WFFs. 1. Example, C, A, C, B, or equivalently, C, A, C, B. Well-formed formula, WFF, for first-order logic. A constant, true or false. An atomic formula, a relation symbol applied to one or more terms. Example, NHBR, X, F. A negation of a WFF. A conjunction of WFFs. A disjunction of WFFs. An implication of WFFs. A universal quantification of a WFF, X. Example, X, NHBR, X, F. An existential quantification of a WFF, X. Example, X, NHBR, X, F. 179. Download for free at https://contents/383D4B872D7B454E99FE2EAA43A8FF at 2020.